Welcome back. In the last session, we covered all oscillators and I gave you the figure of merit of crystal oscillator, and I told that I'll tell you the conclusion part. Okay, the crystal oscillator observations, it is going to give you highest frequency stability, but it is also giving higher frequency range of oscillations, but not like in the order of gigahertz. Okay, now write down conclusion. Before conclusion, write down observations, then I'll give you conclusion. Okay, can you erase this? Because you already copied, right, from the last session. Okay, now observations. Write down the first observation. Hartley and Colpitt's oscillators. Hartley and Colpitt's oscillators. Hartley are, not and, you can say are, Colpitt's oscillator. Hartley or Colpitt's oscillator is giving highest frequency range of oscillations. Is giving highest frequency range of oscillations. Highest frequency range of oscillations in the order of gigahertz. Okay, what it may be. Highest frequency range of oscillations. Hartley or Colpitt's oscillators are providing highest frequency range of oscillations. Okay, which is basically tank circuit, your LC circuit. Okay, without any resistor. That is the reason it is giving maximum frequency, because the gain requirement is very less. If gain requirement is very less, we can get maximum bandwidth from the transistor. And that too, we don't use any amplifier, explicit amplifier. Therefore, the bandwidth of amplifier is limited. We use only transistors that in cross-coupled states. Therefore, maximum bandwidth we can get using FT, or whatever FT each transistor is having in cross-coupled structure. That is what is going to give you maximum frequency, because we don't need much gain. Number 2, second observation. Crystal oscillator. Crystal oscillator. Crystal oscillator. Crystal oscillator is giving highest frequency stability of oscillations. Crystal oscillator is giving highest frequency stability of oscillations. 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 Okay, these two are the observations what we had seen from 4 different types of oscillators, right? RC phase shift oscillator, Wien bridge oscillator, they were the starting oscillators. People started from that, then added whatever they want, then improved, then finally we got the observation Hartley and Colpitt's oscillator, or Hartley or Colpitt's oscillator giving maximum range of oscillations, and crystal oscillators giving maximum stability. Then what is the conclusion? Conclusion. If you observe clearly, it is almost similar to the way or the methodology what we are following. If you take, maybe I'm going back to BJT amplifiers. In the case of BJT amplifiers, what we have seen different configurations. How we were seeing different oscillators, similarly different configurations. Remember, for any technique, whether it is oscillator, or amplifier or regulator, anything, a clipper or a clamper, right? Whatever it may be, if you take a particular topic, there are multiple solutions. We should know all the solutions, and based on the application we need to pick up one of the solutions, and then maybe you can combine and then we can generate a new one, and that is what is your best case, right? In the case of BJT amplifiers, I told that CE amplifier that was giving very good voltage gain but no impedance matching for voltage amplification. CC amplifier that was giving very good impedance matching for voltage amplification but there was no gain. Then what we did, we combined both of them. We got gain from common emitter amplifier, we got impedance matching from CC amplifiers by inserting CC at the input and CC amplifier at the output, right? Similarly, what is the conclusion? I want highest frequency stability. Use crystal oscillator to get highest frequency stability. And I want highest frequency range of oscillations. Use Hartley and Colpitt's oscillator. Therefore, combine both of them, that will give you both stability as well as, I can say, highest frequency range of oscillations. Write down, that is the conclusion. Let us combine both crystal oscillator and LC oscillator. People call it as LC oscillator. LC means it could be Hartley oscillator or it could be Colpitt's oscillator, right? This is what people call it as LC oscillator, okay? It can be called as LC oscillator, whatever it may be, right? Combine both crystal oscillator and LC oscillator to get frequency stability, from crystal oscillator and frequency range from LC oscillator, right? Therefore we are going to combine, okay? That is what it is. Let's see what is that called and what is the technical name. That is what I'll explain, okay? Take it. Then after that I'll give you what is the combination, how are we going to get it, okay? Done? Okay, because I dictated already, no need to wait here, okay? Done. Let me combine. But before explaining this, let me ask you a question, then I'll come to the conclusion part, okay? How to implement it and what is the technical name of it, okay? What is voltage amplifier? You know it, right? What is voltage amplifier? If you take voltage amplifier, let us say this is what is your voltage amplifier, right? This is your voltage amplifier. Therefore, what is voltage amplifier? I am not bothering what is there inside. Just simply, this is your output, right? V0. What is input? Vi. When I say current amplifier, current is input, current is output. Fine. When I say voltage amplifier, let us say voltage gain. Let us say your voltage gain A is equal to 100. What does it mean? When I give 1 millivolt peak to peak voltage signal, let us say I am giving 1 millivolt peak to peak voltage signal, then if it is having gain of 100, I will get 100 millivolt peak to peak voltage signal, right? I will get 100 millivolt peak to peak voltage signal, 100 millivolt peak to peak voltage signal. Therefore, this is what your voltage amplifier, right? It is what is voltage amplifier. but it is supporting any load. Means it is supporting power also. I'm not going to those details. Okay, 1 millivolt peak to peak if you are giving, we are getting 100 millivolt peak to peak to the load. Therefore, how whatever DC power supply you have, right, the DC power will be converted into AC power under the guidance of input AC signal. That is what is your voltage amplifier. Even though you are speaking about voltage signals, but indirectly or inherently it has power gain. Without power gain, we cannot get voltage amplification, and we should not say that voltage amplification. I already explained step-up transformer. If you take step-up transformer is also going to give you, if you have N2 by N1 is equal to 100, step-up transformer is also going to give you voltage amplification, but that is not having power gain. Without power gain, whatever voltage amplification you have or current amplification you have, that is not considered as an amplifier. Default, inherently, even though you are looking for voltage signals, ultimately, but remember inherently it has power gain. Without power gain, that is not called as voltage amplifier or current amplifier or transconductance amplifier or transresistance amplifier. Okay, that I already explained. We invested more time there. That's fine. Similarly, this is what is one, which is voltage amplifier. Voltage as input, voltage as output. Number two, do you have anything called frequency amplifier? Did you hear any time? Frequency amplifier. Did you hear any time? Now what is output? Output frequency. What is your input? Input signal frequency. What is frequency amplifier? Let us say my frequency amplifier. Let us say gain of frequency amplifier K. Let us say K is equal to 100. What does it mean? I am giving, let us say Fi is equal to, let us say it is 1 megahertz. If I give 1 megahertz or let us say 10 megahertz, I am giving 10 megahertz sine wave at the input. Then I am not speaking about output peak to peak divided by input peak to peak. I am not speaking about voltage amplification. I am speaking about frequency amplification. What is frequency amplification? Whatever input signal frequency you have, I want 100 times of output signal. That is what is having the frequency. Therefore, if you calculate what is F0, this is Fi, then what is your F0? Your F0 will be equal to 100 into K into Fi. Therefore, that is K into Fi, which is nothing but what? This is nothing but 100 into 10, 1 gigahertz. Right? This is nothing but your frequency amplifier. Therefore, what do you mean by frequency amplifier? You give some input signal, then if it is having gain, frequency gain, which is nothing but 100 into your input signal frequency is nothing but your output signal frequency. Then why it is very important? Here this is what is voltage amplifier, and then we have seen, everybody knows, using op-amp, using BJT, using MOSFET. But now what do you mean by frequency amplifier? Frequency amplifier is nothing but what? This is with respect to time crossing. Therefore, let us say this is what your 10 megahertz. Okay, this is what your 10 megahertz. This is what your input signal frequency it has. It is not voltage. What is the time period? This is what your time period. Therefore, in this time period, right? Therefore, what is Fi? Let us say input signal frequency is equal to 1 by T. Now, what is your output now? Your output will have in the same time, let us say this is what your time. In the same time, if you calculate in the same time period T, this is the input, right? I am not speaking about output peak to peak voltage. Ultimately voltage signal only, but I am looking for crossings of your signal. That is what is frequency information. Therefore, if you ask me in this time T, 100 times means you will be having the signal, etc. This is what is having. Then if you calculate the time period, output signal, this is what is input signal time period. This is input signal time period. Then if you ask me, this is nothing but your T0, your T0 is equal to Ti divided by 100. Therefore, your F0 is equal to 100 times of your Fi. Therefore, within the input signal frequency, within your input signal frequency, within a time period of T, there are 100 sinusoidal signals. That is what we are expecting at the output. That is what is called frequency amplification, right? That is what is called frequency amplification. Do you have frequency amplifier? And you know, I need frequency amplifier. That is what the conclusion we had seen. What was the conclusion? Combined crystal oscillator and LC oscillator, right? Let me tell you. This is what is a crystal oscillator frequency. If I give input as crystal oscillator frequency, let us say this is what is a crystal oscillator input, crystal oscillator output. That output you are giving it to your frequency amplifier, let us say. But how to get the frequency amplification, I will tell you. We know that this is what is, whatever 10 MHz you are giving, that is 10 MHz only, that is not having any variation. If this is 10 MHz, that is what is coming from crystal oscillator. And let us say it is having constant gain, the frequency gain, which is what is K. People call it as KVCO, which is nothing but your voltage controlled oscillator frequency gain. But what are, maybe I'll explain what is that. Therefore KVCO or K, then what is your output signal frequency? Your output is nothing but your LC oscillator output. Your LC oscillator output. Your LC oscillator output. Therefore, we know that LC oscillator output is having higher frequency of oscillation, but it's not having any stability. To have stable output clock from LC oscillator, take a crystal oscillator output as a reference, compare or sample your LC oscillator output and then compare with crystal oscillator output, or that is the input. Then you see if there is any variation, if there is any change in output, then compare with crystal oscillator output which is stable, then give some error signal. That error signal, if you give it to some voltage controlled oscillator where it changes the frequency of your oscillations by changing the capacitance or inductance, right, then we can control your output signal frequency variation. If there is any variation, that can be controlled because your crystal oscillator output is having stable clock. Therefore, this is what is having stability. Whatever stability you have at the input, that is what is given to stability to your output from LC oscillator. Therefore, that is the reason why we need VCO, voltage controlled oscillator. If there is any deviation from your output signal, which is what is higher frequency of oscillations, LC oscillator output, then you sample it, then give it to or compare with respect to crystal oscillator clock. Then if there is any deviation, if there is any change with respect to your input signal, will have some divider to match to your crystal oscillator frequency. Then if there is any deviation, that will be given to phase detector. Phase detector will detect it and then give you some signal to your error amplifier. Error amplifier will detect or will take that phase detector output and then give you some error voltage. That error voltage will be given to your LC circuit or VCO, voltage control oscillator. Therefore, it will tune the capacitor such that your output signal frequency will not be changed, and it will give you higher frequency of oscillations from LC circuit, and the variation is controlled by your crystal oscillator. This is what is having feedback. Remember, if you want to control anything, not only voltage, that is what we are going to see from regulator, and that is what we are going to see power supply or regulator. Anywhere, if you want to stabilize your voltage gain, if you want to stabilize your operating point, if you want to stabilize your op amp, wherever, whatever, there is always feedback, negative feedback. Therefore, using negative feedback, we can stabilize any parameter, not only voltage gain, not only Q point, not only operating point, right? Not only stability factor, not only current, not only power, not only frequency, not only power supply voltage. Anything can be stabilized using negative feedback, but which parameter you are concentrating on, corresponding feedback should be applied. Therefore, we can get stability. I hope everybody understood. You know what is the technical name of frequency amplifier and then having feedback? Therefore, the frequency amplifier and then feedback, if you add, this is nothing but, this is what people call it as, right, the frequency amplifier with feedback. Frequency amplifier with feedback, with the negative feedback, Feedback is for frequencies, not for voltage signals, okay? Frequency amplifier with a negative feedback. This is what is called PLL, phase lock loop. This is what is technically people call it as PLL, which is phase lock loop, which has LC oscillator internally, that is core of your PLL, and crystal oscillator output, that is the input to your PLL, and we have phase detector, divider, error amplifier. Error amplifier is nothing but low pass filter. Then finally it is going to control your output signal variations, okay? I'll explain the block diagram of PLL, then with that I will say your oscillations are over, okay? A conclusion. Remember, this is what people use practically. When I say serial I/O 5 Gbps of USB data, USB 3.0, remember the clock which we need to send the data of 5 Gbps, that is nothing but 2.5 GHz. From where you are getting that 2.5 GHz? We get it from PLL. People use practically PLL, which is phase lock loop, right, which has two oscillator configurations. Number one, crystal oscillator. Number two, LC oscillator or Hartley-Colpitts oscillator. Okay, you take it, then I'll give you PLL block diagram. This it is done. Then we can go for workbook problems, classroom workbook problems. Okay, take it. Done? Okay, let me explain PLL block diagram. Okay, now PLL. Okay, I'm just giving you block diagram. Few things I'll explain qualitatively directly. Okay, now the first one is nothing but voltage control oscillator. Therefore, before drawing what is voltage control oscillator, right, let me explain what is VCO. It is tank circuit only. This is nothing but VCO. What is VCO? Let us say this is what your amplifier, Hartley Colpitts, right? This is what your cross coupled amplifier, and this is what is your inductor, and this is what your capacitor, whether split inductor or split capacitor, it could be anything, right? Therefore, let us say this is what your circuit. Okay, then this is nothing but your inductor L, and this is what is C, right? If you tune your capacitor, whether you are tuning like coarse way or fine way, I am not explaining those details, but if you tune, then tell me what your resonant frequency. Your resonant frequency F0 is equal to 1 by 2 pi L into C. This is what your resonant frequency, right? Is it correct? 1 by 2 pi root LC. Maybe if I do any mistake, you please correct it. Maybe it is 2 pi root LC. Okay, I think, did I explain 1 by root over 2 pi LC? Maybe if I explain 1 by root over 2 pi LC, please correct it. Only root is there for LC circuit, because 2 pi F0 is omega naught. Omega is 1 by root LC. Not, it is not 1 by root over 2 pi LC. If I do any mistake, you please correct it. Okay, that's fine. Now F0 is equal to 1 by 2 pi root LC. When I say this is what is root LC, if you tune your capacitor, right, after or by tuning your capacitor by tuning in nothing but changing the frequency. By tuning C, right, we can vary F0 to required frequency, to required oscillations. Okay, nothing else, voltage controlled oscillator. But how will you change the capacitance, right? How will you change? Therefore, this is what you can take. We can take variable capacitor. Therefore, the capacitor can be taken as variable capacitor, which is controlled by voltage, which is controlled by voltage. If it is controlled by voltage, then this is what is voltage controlled capacitor. If it is voltage controlled capacitor, then this is what is varactor. Sorry, not varactor. Yeah, variable capacitor. This is what is called varactor. Then this is what your varactor. But how will you get varactor? Not only PN junction diode, we can use your MOSFET also, right? And we can use metal finger capacitor also. There are many ways. That's what I'm saying. I'm not going into the details which one practically people use, not PN junction diode, but we can use PN junction diode when it is in reverse bias. When you change reverse bias voltage, its capacitance, transition capacitance will change. But normally people don't use PN junction diode. People use either device or metal capacitor, etc., etc. With the switches, so many things, but this is ultimately variable capacitor with respect to voltage. If it is function of voltage, therefore this is what is function of control voltage. Who is giving that control voltage? That is what I'll explain. Some control voltage, or people call it as error voltage, whatever it may be. That control voltage will tune your capacitance. That is what is going to give you the frequency of oscillations. Okay. Now we know what is VCO. Now what is PLL? Just listen. This is what is the core of your PLL is nothing but VCO, voltage control oscillator, VCO. Okay. And this is what your output. Okay. What is VCO output? Sine wave. Okay. Now I want to divide it. If I want to divide it, this is what people use, divider. Okay. Now this is what is sine wave. Internally people convert into sine to square wave, because we cannot divide sine signals. We have to convert into square wave, right? Then that square wave can be divided with what ratio, whatever you want. There is algorithm to have the division. I'm not going into the too many details. Then there is something called, it is nothing but a comparator or phase detector. That is what people say. This is nothing but a phase detector. It is going to compare the two phases of your input signal and the feedback signal. This is what your feedback signal, and the output. Whatever phase difference you have, that is what is going to give it to error amplifier or low pass filter. This is basically your low pass filter or error amplifier. Then indirectly the phase will be converted into phase error. Phase error will be converted into voltage. That voltage will be given to your capacitor. Then capacitor value will change. Then the frequency will change. Okay. And this is what your reference clock, reference crystal clock or crystal oscillator clock, right? If this is what your reference and this is what your feedback clock, this is your feedback clock, then it is going to compare. Remember, we cannot compare sine waves because this is digital in nature. The reference crystal oscillator clock will be converted into square wave. Those things I am not showing. Therefore, it is converted into square wave. Whatever sine wave which you are getting from VCO, then convert into square wave. The square wave will be divided. Therefore, maybe for your understanding, what I can do, this is what the arrow is indicating the direction. This is not a feedback circuit. This is what your feedback, and this is what is sample, and this is what your output. Therefore, this is what we are looking for. Your output F0. It is not resonant frequency here. Resonant frequency only, but output frequency. Okay, and this is what your input signal frequency, right? This is Fi. Your input signal frequency, and this is what reference clock or input frequency, and that is what your output frequency. Therefore, now tell me, let me explain. Just listen, don't write anything. Right? Now, for example, your reference clock is 10 MHz. This is 10 MHz, right? 10 MHz CMOS clock. That's what people say. Okay, this is 10 MHz. Then let us say the KVCO. This is what is having the gain. That is what people say KVCO. Let us say KVCO is equal to 100. I'm just taking one example. Then whatever signal you are having, 10 into KVCO, let us say 100, let us say I'm expecting 1 GHz. This is what is I'm expecting. And remember, whatever gain you have, that much division you need to have. Therefore, here it is divided by 100. Therefore, your reference will be, the feedback clock will be divided by 100. Therefore, what is the division here? The division is by 100. Therefore, 1 gig by 100 is nothing but again 10 MHz. Therefore, this is what is your feedback clock 10 MHz. It is going to compare, and if there is no difference, therefore here this is what is phase error. Whatever phase error, that is what we are getting here. Now the phase error will be converted into error voltage. That error voltage or control voltage. That voltage will be given to your voltage controlled oscillator. Then it is going to tune your F0. Okay. Now just listen. Under steady state, right? Under steady state, this is 1 GHz, this is 10 MHz, this is 10 MHz, this is always constant. Then 10 MHz to 10 MHz, no difference, no phase error, no error voltage, no change in control voltage, there is no change in the F0. Fine, fantastic, fine. But due to any reason, if F0 is changing, if F0 is changing, what I mean is, let us say, what is phase detector? If you take phase detector, this is what your phase detector. Phase detector is nothing but what? Whatever reference clock you have, let us say this is what your reference clock. Okay. Now the feedback clock, right? This is what your reference clock. And let us say the feedback clock is also having exactly the same phase. means same frequency, right? Then this is what your feedback clock. Now due to any reason, if due to any reason, then what is the error? The error is 0. Therefore in this case, what is the error? Phase error. Phase error. Phase error is 0. There is no error. Therefore this is 0. There is no error. But now if there is any error, you know, phase detector without error, right? Therefore without error. Now if you take phase detector with error, that is nothing but your correction. That is what is having some correction. Let us say this is what your reference clock. This is what your reference clock, and this is your reference clock. Now just listen. Due to some reason, your F0 is increasing. When F0 is increasing, right, definitely your feedback clock also will increase. Mean the frequency of your feedback clock will increase. The frequency of feedback clock is increasing. What does it mean? Whatever you have, rising edge, let us say, that is what is having, it is increasing. Okay. Therefore, let us say this is what is decreased. Okay. This is what your time period. This is what is decreased. Okay. This is what is decreased. The frequency is decreased. Okay. This is with respect to reference, what it may be, right? Therefore, this is what your time period. This is expected time period. This is expected time period, the reference clock. But now, what is your time period now? Now, the error. There is a time period. This is feedback time period. This is what is your feedback time period. This is a reference clock time period. Therefore, now see, if frequency is increasing, then it is divided by 100, then it is more than 10 MHz. If it is more than 10 MHz, the frequency of your feedback clock is decreasing. When the frequency is decreasing, there is error, right? Then if you see rising edge to rising edge, therefore this is ideal clock, now this is what your ideal clock. Therefore same rising edge to rising edge, what it may be, right? Now ultimately this is what is having some variation. Therefore the rising edge of this is having some variation. Then tell me what we get at the output. You will get some variation, what it may be. Ultimately it will track. When it is tracking, right, phase detector will detect the phase difference. Whatever phase difference you have, it will detect. This is what your phase difference. Again there is a phase difference here. Whenever there is a phase difference, it will detect. Okay. Whenever there is a phase difference, it is detecting. Therefore this is what is your feedback clock, and this is what is your phase error. It gave some pulses. Pulses means wherever pulses are there, there is some phase error. Phase error means the phases are not aligned. Here the phases are aligned. Whatever phase you have from reference clock, the same phase is expected from feedback clock, right? Here rising, exactly aligned, therefore there is no phase error. But here, because due to some reason, due to temperature or due to coupling or whatever it may be, there is a change in the frequency F0, that is increasing. Then your feedback clock frequency is also increasing. Then the period is decreasing. Then there is an error which is what is created. That error is detected by phase detector. That phase detector error will be given to low pass filter. Very simple. If you have more phase error, the width of the phase, which is what is generated from phase detector, will be more. If you have more width, what is low pass filter? It is simply RC circuit or error amplifier, right? Then what it will do? It will give you the output voltage, right? If you give it to error voltage, now error voltage, right? Now if you calculate the error voltage, if there is nothing, your error voltage will be 0. Your error voltage, it won't change, it is constant. But now whatever constant you have, this is what your error voltage. Okay, what is voltage you have? Because it is high, it will be charged. It is trying to charge, but now it is gone. Now I can say again, there is a error, it will be charged. It will be charged to that, and it will stay. And again if there is error, again it will be trying to charge. What it may be, there is error voltage that is given to a RC circuit. The capacitor will be charged, then it will not discharge immediately, then it is holding, and the next phase whatever you have, if that is what is having, then slowly what will happen, that is what is going to increase. If the error voltage is increasing, that voltage is given to your capacitor. When that is what is going to give to your capacitor, then the voltage is increasing. When the voltage is increasing, let us say, or decreasing, whatever may be, whatever error voltage direction you want, you can get it. That is what is going to give you the feedback, the type of feedback. Therefore now tell me, if that is what is increasing or decreasing, let us say if C is decreasing, therefore whatever F0 we are having, let us say the error voltage whatever it is increasing, if that error voltage is controlling, or I can say capacitance is increasing, therefore due to which as error voltage is increasing, as error voltage, let us say, that is increases, let us say the C is increasing. When C increases, what about resonant frequency? F naught is equal to 1 by 2 pi LC. When C is increasing, your F naught will be decreasing. It will be controlled back. Due to any reason, if F naught is increasing, the feedback will come into picture, but how many clocks of your reference clock is taking, or how many clocks or how much time it is taking to settle, I am not speaking those things, but ultimately under steady state, it has to. That is what is depending on the stability. Again, it is a loop, but that is for frequency stability. I am not going to those details. Therefore, now when F naught is decreasing, then it will be controlled. Ultimately, it has to come to 1 GHz. This is what is our PLL. Therefore, what is the abbreviation? Phase lock loop. This is what is the loop, which is what is trying to lock off your feedback clock. Sorry, the phase of your feedback clock is trying to lock to your reference clock or crystal clock. Because we know that your crystal clock is absolutely stable or almost stable, then whatever feedback clock, if it is trying to track to your reference clock, then feedback clock is stable, then your output is stable. Only if output is stable, then only feedback clock is stable. If feedback clock is stable and then matching to reference clock, then there is no phase error. If there is no phase error, no error voltage. Then there is no tuning, therefore there is no change in F naught. But due to any reason, if F naught changes, this loop will come into picture to correct or to have the phases to be aligned. Then until the phases are aligned, we cannot get it. Then you know what will happen? As F naught is decreasing, then your feedback clock frequency will decrease, means slowly it will be opened up, slowly the voltage, the phase error voltage will decrease by having smaller pulse width. Ultimately the pulse width will become 0 and then it will become phase error to 0. Okay, this is what is more than enough. Now how to get the phase error? This is simply exclusive OR gate. This is 1, this is 0, you will get it. 1 1 0 0 0 0, again 1 0 0. Therefore simple form, wherever if you want to find only rising edge, not falling edge, right, then you can go ahead with simply exclusive OR gate. But as we go on, the complexity will be increasing based on the requirements as we go to higher frequencies. Okay, this is what is more than enough for us. If anybody is asking related to VCO, then KVCO is nothing but your frequency amplification gain. But remember, KVCO is nothing but input is voltage and output is frequency. Okay, but overall, if you ask me, what is input? Crystal clock frequency. What is output? Your LC oscillator or VCO output frequency. Overall, what is the gain? The gain is nothing but I can say around 100. Right? Here the KVCO is not related to VCO only. I can say overall gain. Therefore, instead of saying KVCO 100, let me correct it. It is not KVCO. KVCO is different because that is a relation which is what is giving you error voltage to output voltage, output frequency. But now this is nothing but your gain frequency or the frequency gain. You can say the frequency gain. The frequency gain. You can say that is what is for your amplifier. What is your amplifier? If I take this is what is your overall having feedback. Okay, having frequency gain 100, right? This is what your feedback, and now whatever reference clock which we are getting, that is what we are getting from outside. This is what is from crystal oscillator. Therefore, crystal oscillator will give you the clock. Okay, this is your crystal oscillator. That is the input. Okay, but there is something in between. It can give directly CMOS clock, what it may be, right? The phase detector will work with CMOS. This is also kind of phase detection. Then error voltage, analog voltage. That analog voltage will be converted into sine wave. The sine wave will be converted to square wave. The square wave will be divided. Then these are all square waves. Those things I am not explaining, but you can take it. Okay. For VCO, input is voltage, output is frequency. Okay, that is what is the gain. People call it as KVCO, change in output frequency with respect to change in input voltage. That is what is called as KVCO. That will determine how much range it can correct. Okay, but this is what is the block diagram to understand, to start with. It is having negative feedback for frequencies. Okay. See, whatever Hartley oscillator, Colpitts oscillator I explained, right? Here this is sine wave. You will get sine wave, but we have to convert into, maybe inside you can take it. The sine wave will be converted into square wave. For the square wave only we can have division. That square wave and whatever crystal oscillator you are getting, that should be converted into square wave. That square wave and this square wave will be detected with phase detector. Then you will get a pulse, something like this. Then whatever pulse you are having, that is converted into a voltage. The voltage will be converted to sine wave, again sine wave to square wave. But if you want to shift sine waves directly, that is what people call it a CML clock. Therefore, common mode logic clock. Therefore, the sine wave can be directly sent to the circuits whatever clock is needed. Means whatever circuit is asking for the clock. But almost time is over. We'll solve classroom problems. You can start problem number 19. Okay. But almost session is over. If I start, it will be in between. Okay. The timing diagrams are important. Actually, if there is any error, means if there is a change in output signal frequency, that is what is coming in the feedback clock. Right? The frequency is increasing, means the time period is decreasing. Then immediately there is an error, phase error, that will be detected by your phase detector. That will be given to your error amplifier. This low pass filter is also called as error amplifier. It is going to amplify the error signal. Therefore, low pass filter plus charge pump. There is something called, but whatever maybe this is what you can say effectively, error amplifier. That output is given to VCO. VCO will control and then give you an output signal frequency. So the core of the amplifier is VCO, but it is a kind of open loop. We are stabilizing the resonant frequency which you are getting from VCO, that we are using feedback. And we need reference always. Reference is the one which is what is whatever stability you have in the reference, the same stability you get in the output. Even in voltage regulator also we need reference. Whatever stability you have in reference voltage, the same stability is applied to your output voltage also. If the reference voltage is not having stability, your output voltage, whatever you are deriving based on the reference voltage in the feedback, will not also have the stability, right? But here we have amplification, frequency amplification. Similarly, whatever reference voltage you want, you can get it. Okay. For example, if you want directly 10 MHz, that is what is enough for me, then no need of PLL. Directly you can drive the crystal output with some buffer amplifier. Directly you can drive your 10 MHz to your circuits, whatever you need. That is what earlier people used to do. If you take 8085 microprocessor, 8086 microprocessor, maybe when you do your microprocessor lab, did you see microprocessor kit? Then the microprocessor exactly on top of top left corner of your microprocessor, if you see top portion, you will see some metal can capacitor. That is nothing but crystal capacitor, and then amplifier. That amplifier, open loop amplifier of crystal capacitor will be there inside your microprocessor. Combinedly, that will give you crystal oscillations. That is what is having highest frequency stability of oscillations. But wherever you want higher frequency, it is kind of amplification, frequency gain, frequency amplification. Then we have to use VCO, and to improve the stability, we are using feedback with a reference clock as crystal oscillator. Okay, that is what it is. This is done. Maybe you can continue, and the time is not enough to solve the problems. We will continue for the classroom workbook problems right, in the next session. Continue. Thank you.